Okay, so this is section 2.8, number 4. We have y double prime plus lambda y equals 0. We have two conditions. Again, they're endpoints because they're at different spots. Y prime of negative pi equals 0 and y prime of pi equals 0. So sometimes your initial conditions just have y, but other times they have y prime. And you can have one of each, too. You could have a y at this end and a y prime at that end. That can all happen.
Oh, negative.
Yeah, y prime at negative pi. So there are two different conditions there. Okay, so the directions when you go to take your test. Question number 1 will be, is lambda equals 0 an eigenvalue, yes or no? Well, if lambda equals 0, we have the equation y double prime equals 0, which has solution of y equals ax plus b, because you have to integrate twice. Given these two initial conditions, do you get a non-trivial solution? Well, what has to happen? We know if we take the derivative, y prime is a. We know y prime at negative pi has to be 0, but y prime at negative pi is also just a, isn't it? Because there's no x to plug in. And by the same token, we have y prime at pi equals 0, but that's also a. So we're very convinced that a has to be the number 0. What about b? Our initial conditions don't force b to be 0. Do we want b to be 0? No, we would like b to be anything but 0. Why would we want b to be anything but 0? Then it would be a non-trivial solution. We might have, for example, y equals 3.
Actually, I think b is anything but 0.
That's right. B can be anything but 0. You're left with, because a has to be 0, you're actually left with the equation y equals b, but our initial conditions don't force anything on y equals b. So lambda can be 0. So lambda equals 0 is an eigenvalue. And the associated eigenfunction is y equals b, as long as b is not the number 0. So y can be any number in the world you want it to be, except the number 0.
So pretty much, so lambda is what's inside like the box. So is lambda...
Lambda is just a number that's right here. So what we want to discover all the possible values for lambda so that this equation has non-trivial solutions. So far we found one answer. One answer is lambda could be the number 0. If lambda is the number 0, we can have a non-trivial solution. Now we want to deal with what happens if lambda is positive. Well, then we have y double prime plus lambda y equals 0. That's r squared plus lambda equals 0. So r is plus or minus I square root of lambda. And just because I want to be a little bit lazy, I'm going to have to write the square root of lambda a lot. I don't want to write that symbol. It's kind of a pain in the neck to write. Give me a different letter. L. L for square root of lambda. All right. So, well, it would be L times I, correct? So this means my solution would be y equals C1 cosine Lx plus C2 sine Lx. And this is why I didn't want to write square root of lambda, because the next thing I have to do is take derivatives, which means I'd have a whole bunch more square root of lambdas. It just gets to be a pain in the neck to write. Let's just call it L. Okay, so I take my derivative so I can plug in my initial conditions. Y prime is negative C1 times L sine Lx plus C2 times L cosine Lx. Plug in my two initial conditions. I have 0 equals negative C1 L sine of L times negative pi plus C2 L cosine of L times negative pi. Okay? Where's the negative pi? I'm plugging in negative pi.
Oh, okay.
That was one of my initial conditions. Now I'm going to plug in positive pi and get my equations. If I plug in positive pi, I get 0 equals negative C1L sine of L pi plus C2L cosine L pi How do you solve? Remember, what are we trying to find here? No, we don't really want to find C1 and C2. We really want to find L, because if we find L, that'll tell us the value for lambda. So we really don't want to solve for C1 and C2. We really want to solve for L.
We can't have any number greater than 0.
Well, my question would be, pick a number that you like for lambda. Or for L, I mean. For L. So if I plug 3 in for L, I would have 3 pi here, which would be 0.
Square root of 3 pi.
Oh, it would be square root of 3 pi, which is not 0. And if I plug 3 in there, I have
No.
cosine.
L equals the square root of lambda. It doesn't equal lambda. So if L equals 3, then 3 equals the square root of lambda. So 9 equals lambda.
Okay, so you want L is 3,
Yeah.
and we'll worry about lambda later. L is the number 3. If I plug the number 3 in here, I get sine of 3 pi. Sine of 3 pi is 0. But if I plug 3 in over here, I'm going to get cosine of 3 pi. That's not going to be 0, is it? So altogether, is that going to add up to 0?
No.
Well, what if C2 was the number 0?
Huh.
So if C2 is the number 0 and L is the number 3, we get an answer.
Wait. 3 comes from where? Again,
3 came from Jesse's brain.
Okay.
Jesse said L can be any number you want. And so I said, okay, pick a number.
Okay.
And he picked 3.
So this is why we get to take the perfect roots, because it's the square root of lambda equals L. Therefore, any whole number we pick then becomes perfect root. If we change back into lambda.
Well, if I plug in 3, 3 will work as long as the number C2 happens to be the number 0.
Yeah, but if we pick an even number, C1 would have to be 0 and C2.
If I picked an even number, then I would get 0 over... No, I wouldn't. I'd get 0 here still, wouldn't I?
So no matter what I pick for L, it's going to be a perfect root.
Okay, but who said L had to be a number like 1, 2, 3, and 4? Why couldn't L be 5/8? Who made the rules that L can't be fractions?
Oh my God.
Or maybe L could be pi itself. Ah, rats, huh? Just got harder. All right, so what I think we need to do is, I think we need to do some work. So we have found that there are some answers, however, didn't we? We have discovered by trial and error that if L is a whole number, like 1, 2, 3, 4, 5, and C2 is 0, then we do get solutions. But my question is, are those the only solutions? No, I hear votes for no. You got other solutions?
If C1 is 0, L can be like a half number, so like 3 halves or 5 halves.
Ah, excellent. If L is a number like a half, what's cosine of pi over 2? 0. So if L is a half, then we would need C1 to be 0. So L could be a half or 3 halves or 5 halves. So there's a whole bunch more answers. So now the question is it possible for L to be a different number? L to be, say, maybe 3/8, and the whole thing will add up to 0, and C1 and C2 maybe aren't the numbers 0. So I guess my question is, are there more answers still? What's that?
Unlimited.
Unlimited. Well, no. Well, there are an unlimited number of answers. There are an infinite number of answers. 1, 2, 3, 4, 5, 1 half, 3 halves, 5 halves, so on and so forth. But are there more answers than that? I think the answer is no. What I would really like to do is I have a system of equations here. I'd like to do the kind of elimination that we usually do. But it seems as though I can't, because this one has a minus pi and that one has a positive pi. And that one has a minus pi and that one has a positive pi. I'd really like to change that so they both have positive pi's. Can I do that? Yeah?
Yeah, sine may pull out and cosine doesn't matter. Maybe it's the other way around.
You're absolutely right. Sine is an odd function. So sine takes this negative sign and brings it out front, which means if I change that to a positive, it also changes that to a positive. Sine is an odd function. Cosine, on the other hand, is an even function. What does cosine do to negative signs? It just kills them. For example, the cosine of pi over 4 and the cosine of negative pi over 4 are the same. They're both square root of 2 over 2. So I can change that one to a positive. So there's a little trick you're going to have to use sometimes when they give you initial conditions and your initial conditions have negative values. You have to use the fact that sine and cosine are even and odd. Now look what I can do. I can go ahead and I can just add these two equations together. And what happens? I get 0 equals, the signs cancel out. I get 2 C2 L cosine L pi. Well, I don't want C2 to be 0 because I don't really want to come up with trivial solutions. What numbers do I want for L here? Cosine of what gives me 0? Fractions, pi over 2, 3 pi over 2. So L could be 1 half, 3 halves, 5 halves, so on and so forth. But at the same time, I would have to have C1 would have to be the number 0. So that this piece also disappears and my whole thing equals 0. Conversely, we already actually answered the question. What happens if C2 is the number 0? Well, if C2 is the number 0, that whole part of the equation goes away, and we already discovered that L would have to be whole numbers 1, 2, 3, 4, 5. So L would have to be 1, 2, 3. Okay, there you go. Okay, so here are our eigenvalues. Lambda could be, what does it have to be? If L is a half, then lambda would have to be a half squared, which is a quarter. So lambda could be a quarter, it could be 9/4, could be 25/4, so on and so forth.
And where are you getting the fourths from?
Because remember that square root of lambda is L. So if I want to get lambda all by itself, I have to square both sides. So when I square a half, I get a quarter. When I square 3 halves, I get 9/4, so on and so forth. So it's still the perfect squares type pattern, except you got to divide by the 4s this time. And my associated eigenfunction, in this case, would be y equals, what would my associated eigenfunction be? C C2 sine lambda x, square root of lambda x. Because remember, when we're using these numbers, C1 has to be 0. So I got to plug C1 equals 0 into my original equation, not into my derivative. That's an easy mistake to make. When I plug C1 equals 0 there, the cosine one disappears, the sine one survives. Or the other possibility, if L is 1, 2, 3, 4, then lambda is 1, 4, 9, 16. And then Y would be C1 cosine square root of lambda x would be my associated eigenfunctions. So you get different types of eigenvalues depending on what happens, which gives you different types of eigenfunctions.
So when you're writing that last part, you don't have to include that as long as C1 equals 0.
Right, because for this part, C1 was 0, so this piece is gone. And for the second condition, C2 had to be 0, which means that half of the equation is gone. Questions on that?